All right, thanks for coming. Thanks for staying late. I'm going to be talking about work in learning theory with Rocco Servillo in a minute. So let's talk about learning. About 30 years ago, Les Valin introduced the PAC model of learning, and looking back, it's really one of the great success stories of theoretical computer science. It's a clean mathematical framework, and yet it closely models the train and test approach to machine learning. And within theory itself, it has rich connections to crypto, to complexity, and more recently to privacy. So it's really a great success story. However, if there's one thing that's slightly disappointing, it's turned out to be an extremely challenging model. There are very few positive results. In the PAC model, the learner does not have any control over the distribution of examples that they receive. So on one hand, algorithms that you design satisfy this extremely strong criteria, which is great, but it also makes it extremely hard to design algorithms in this model. In particular, there are many basic classes of functions, seemingly simple classes of functions, for which, forget efficient, we have simply no non-trivial PAC learning algorithms. So in the next few slides, I'd like to give you a few such examples. So example one is related to half spaces. A basic fact in learning theory is that we can learn n-dimensional half spaces over the Boolean hypercube efficiently in poly-n time. This is by now a simple fact. It follows easily from linear programming, but it's really the basis of almost all known PAC learning algorithms. So that's great. A fundamental class for which we know how to learn efficiently. Let's tweak it a little bit. How about the intersection of two half spaces? Can we do this efficiently? Well, forget about efficient. Our best algorithm for this class is not really an algorithm, it's simply brute force and running in time 2 to the n. Okay, and this is not for the lack of effort. This class has been intensively studied. We'll love to learn this class, but unfortunately, most of what we have is lower bounds showing that negative results ruling out certain approaches to this problem. Okay, good. So that's one example. The second example is Boolean circuits. We know now how to learn depth 2 circuits in time 2 to the n to the 1/3, which is a step towards one of the main challenges in Valin's original paper. So that's great. We can say something about learning depth 2 circuits. Let's again try to tweak it and see if we can learn a seemingly modest extension, depth 3 circuits. Again, in this case, we have no such algorithm. We have no algorithm at all. Our best algorithm is simply brute force and run in time 2 to the n. And again, we'll love to learn this class. This class has been intensively studied. Okay? Good. So let me dwell a little bit more on how frustrating this is. The intersection of half spaces, Boolean circuits, these are not classes, exotic circuit classes that are beyond the reach of current understanding. We sort of have some understanding of these classes. In particular, for about 30 years now, we've had methods of proving strong circuit lower bounds against these classes. To prove these lower bounds, we have developed techniques to reason about their structure. But somewhat frustratingly, we have not been able to leverage the techniques or the understanding to give us learning algorithms, which is especially frustrating. But again, these classes shouldn't face us as complexity theorists. Okay. So in this work, the inspiration for this work is that maybe we're being a little too harsh on ourselves. Rather than aiming for polynomial time or even exponential and root n time, let's study quantitatively how much savings can be achieved over the naive 2 to the n runtime, zooming in on this neighborhood of 2 to the n. And there's a rich hierarchy of running times. The first baby step one can take is polynomial savings, and the next qualitative step one can get is exponential savings. And it would be really nice to get strongly exponential savings, 2 to the n divided by truly exponential n. Okay, and these are all steps towards maybe one day designing more efficient algorithms. As it turns out, this is a fruitful perspective. We obtain a variety of new learning algorithms via powerful lower bound techniques.
One question, when you do this lower bound, you talk about proper learning all the time, right?
No, this is PAC learning, not proper even. Yeah, so the intersection of half spaces, even if not proper, we have no learning algorithms. In fact, for proper learning, we have hardness results, cryptographic, and so on and so forth. Yeah. Okay, good.
For proper learning, you can often just give hardness only assuming that NP is different from RP or whatever.
Yeah, so non-proper learning, we still do not have any non-trivial algorithms. So really stuck. Okay, good. So among our results, let's visit our 2 motivating examples, intersection of half spaces and Boolean circuits. In this work, we can learn not just the intersection of 2 half spaces, which is the n of 2 half spaces. We can learn your favorite function of 100 half spaces with strongly exponential savings. Again, just to recall, this terminology is 1.99 to the n. Okay, and how about depth 3 circuits? Well, as it turns out, we can learn constant depth circuits, depth 100 circuits with exponential savings. So these are just 2 results among are the first learning algorithms for many other classes. Okay, good. So before moving on and describing our results in the proof, I just want to say that while this perspective may be new in learning theory, it's certainly not new in theoretical computer science. It's the dominant view in the study of satisfiability algorithms. Our best algorithm for KSAT runs barely better than brute force. The ETH and the Seth are very influential hypotheses precisely about just how much you can save over 2 to the n. And of course, there's a recent explosion of interest due to connections to circuit lower bounds. And indeed, this line of research is the inspiration for our work to port this very fruitful and successful perspective from satisfiability algorithms into learning algorithms. Yeah.
By the way, learning here means learning to constant error?
Sure, even learning, learning to accuracy 99%. Pack learning.
Yeah, but you have boosting, so if
Yeah.
you can
Sure,
add
yeah,
to the-
fine, yeah.
it doesn't
Boosting,
matter.
yeah, sure. Yeah.
If you can,
So weak learning as well.
if you learn weekly, then you do boosting, and you can learn efficiently strongly.
That's a good point. Yeah, so we're not even able to learn weekly. Yeah, but I'll define the model very carefully in a second. Okay, so let me move on. This connection between circuit lower bounds and algorithms is also present in our work, and a particular unifying theme in this work and in the rest of this talk is that we obtain learning algorithms from circuit lower bound techniques. While this may seem a little counterintuitive at first, I'd like to just say one vague sentence about why it shouldn't be so surprising. What's a circuit lower bound? A circuit lower bound says that a function f is not in a circuit class C, and circuit lower bounds are proved by saying that circuits from a class C are too simple to compute a complex function f. F as, say, parity, and C as the class of bounded depth circuits. And one can often exploit the simplicity of C. To prove a circuit lower bound, you have to prove that class C is simple. You can often exploit the simplicity of C to design learning algorithms for C. And in this work, we're going to design learning algorithms for C. And in the rest of this talk, we'll see examples of this theme, where we take a circuit lower bound and we use the circuit lower bound technique to design learning algorithms. Okay, good. So for the rest of this talk, I'll quickly define our learning model, and I'll touch on learning via two lower bound techniques. The first is the method of random restrictions, very powerful technique responsible for a very precise and sharp understanding of the structure of AC0 circuits. We'll use this technique to learn AC0, and in this case, we'll see the learning results follow quite easily from the circuit lower bound. And the next is a different technique, the so-called Nachiy-Peruk's technique. It's a very general technique that applies to managed circuit classes. It yields the best known lower bounds for numerous models. And again, from our perspective, given this new perspective, we're able to use Nachiy-Peruk's technique to get learning algorithms for precisely all these computational models that Nachiy-Peruk captures. And in this case, unlike the first part, we'll see that there's additional work to get the learning result. And in particular, we have a new learning primitive that could see further applications. Okay, so let me start with the model. It's a very clean, very simple model. We are actually not going to work in the PAC model. We're going to work in the so-called exact learning from equivalence covariance model for two reasons. One is, as we'll see, it's extremely clean, extremely simple. I'm going to be able to fit it in this slide. And second, more importantly, upper bounds in this model. This is a strong model. Upper bounds in this model imply upper bounds in PAC learning. Okay, so here's the model. Learning proceeds in a sequence of trials, and we're concerned with exact learning. Okay, so there's an unknown target function f, what we're trying to learn from a known class C. Think of C as the class of all AC0 circuits, and f as a specific AC0 circuit. The learner maintains a hypothesis H, her best guess as to what f is. Okay, and the learning, as I said, proceeds in a sequence of trials. While H is not exactly equal to f, we're working again with exact learning. Learner is given...
We're excited to have everybody over because we are going all out. I'm not scared. I like to have a little bit of variety of everything.
Good.
And it was the weather channel. Yeah.
Yeah, fantastic. Okay, good. Well, her hypothesis is not exactly equals to the function. She's given a counterexample x, a witness to the fact that she's not done yet, such that h of x is not equal to f of x. She gets to update her hypothesis. She better update her hypothesis, because if not, in the next round, she'll get the same x. And it just proceeds like this until she gets the function exactly correct. Okay, and the running time is just a worst case running time until she gets the function exactly correct. Okay, so it's a pretty demanding model, and it's probably not so surprising that it implies calculability. Okay, good. So that's the model we're working in. Let's start with the first lower bound technique, and we will use this technique to design learning algorithms, in particular for the class of size S depth D circuits that run in time, this running time. So if we think of S as poly n and E constant corresponding to AC0 circuits, then we get exponential savings. Okay, good. So what are random restrictions? Just to quickly recall, when we apply a random restriction to a Boolean function f, we get a simpler Boolean function f hit by rho. It's of course very vague. To make it slightly more precise, a random restriction randomly fixes most input variables to the function to constants. So with property P, it keeps a variable alive, and otherwise it fixes it to a uniform random constant, either 0 or 1. Okay, and we should think of P as small, say 1 over log n. So a random restriction is pretty harsh. It hits the function and it fixes most variables to the function. And as we'll see, random restrictions are useful because it really dramatically simplifies certain functions. In particular, if f is an AC0 function, a random restriction really crumbles the function. So this is formalized in the famous switching lemmas, a long line of work on the switching lemmas which says the following. If f is an AC0 circuit, if you hit f with a random restriction with extremely high probability, f crumbles to a very simple object, a small depth decision tree. Okay, it's very easy to see that a small depth decision tree is a very special structured kind of AC0 circuit. In fact, it's a very structured kind of depth 2 AC0 circuit. Okay, so we have a complex object, we hit it with a random restriction, it collapses to a very simple object with high probability. Okay, and we'll use this, we can use this to prove circuit lower bounds, and in this talk we will use this to design learning algorithms. Good. For the learning algorithm, the following equivalent view of switching lemma is going to be useful for us. What's a random restriction? A random restriction is nothing more and nothing less than just simply zooming in on a random subcube of the n-dimensional hypercube. So you have an AC0 circuit defined on the n-dimensional hypercube. To apply a random restriction to it means to zoom in on its values on the random subcube of the hypercube. Okay? Now switching lemma says that you have an AC0 circuit, which we think of as complex. We do not know how to learn it. When randomly restricted to a subcube, locally, it's actually very simple. It's a small depth decision tree with high probability. Okay, good. So let's use this to learn. An easy consequence of this is that if you randomly partition 0, 1 to the n into these waffles, then for most of the subcubes, for the vast majority, corresponding to with high probability, locally, the AC0 circuit on that subcube is actually a very simple function, a small depth decision tree. Of course, this is not going to go for all subcubes. It's going to remain complex on a tiny fraction of bad subcubes. But that's fine by us. Okay, so we're good on most subcubes, and why is this useful in our specific context? While we do not know how to learn AC0 circuits, we do know how to learn decision trees efficiently. Okay, so the switching lemma will be a way for us to bootstrap this learning algorithm for simple objects to learn the complex object, the AC0 circuit. Okay, so let me just state our learning algorithm, although hopefully we can sort of guess what's going to be. Okay, good. So the first step, I'm going to randomly partition the hypercube into subcubes. I'm going to run a separate copy of a decision tree learner on each subcube, just assuming for now that f is indeed a small depth decision tree on every subcube. That's not going to be true, but it's going to be normally true. Okay, so I receive counterexamples. I'm going to invoke my decision tree learner on this subcube. I receive another counterexample. I'm going to start my learning process on that subcube, so on and so forth. Okay, and I keep going. What's going to happen? The learner is going to succeed because you are indeed a small depth decision tree on most subcubes. The learner is going to succeed on the vast majority of subcubes, denoted by green here. Meaning, the learner gets the entire subcube correct after a small number of examples, much smaller than the density of the subcube. Okay, there are certain subcubes, the ones in red, for which this is not true. F is not a simple function. Well, such as life, we'll go beyond this small number of examples and we keep receiving counterexamples. Well, at that point, I'm just going to learn the red subcubes by brute force. Okay, and if you balance parameters, you get what we have, a learning algorithm for AC0. Okay, at a very high level, that's a sketch of how we use the switching lemma, along with a well-known learning algorithm for decision trees to learn this complex class of AC0 circuits with exponential savings. Okay, good. In my remaining time, I'd like to cover the second technique. So we have quickly defined our learning model. We have touched on the first method, the method of random restrictions. Next one is Nash-Brooks technique, which applies to a different class of functions, but it's very general, and we're going to get learning algorithms for all these models that Nash-Brooks technique covers. And in this case, as we'll see, the learning algorithm, unlike the first part, it doesn't follow as easily from the lower bound technique. There's going to be additional work involved to get the learning result. Okay, but let me just explain what Nash-Brooks technique is. Okay, so we're going to use as a representative example, we're going to give a learning algorithm for full basis binary formulas of roughly quadratic size, a binary formula over n or non-n parity gates that runs in time with exponential savings. Okay, this is a representative result. As I said, Nash-Brooks technique applies to many circuit models, and likewise we get learning results for many circuit models. Okay, so let's quickly recall what Nash-Brooks technique says. In the first part of the talk, we saw a notion of simplicity based on subcubes. We'll be dealing with a different notion of simplicity in structure. Previously, our notion of simplicity was that for most of these subcubes in a waffle, the circuit is actually very simple locally. We're not going to have that now. We'll have a different notion of simplicity. Here's the notion of simplicity. In a random partition of the hypercube, there are very few distinct subfunctions. Okay? While these subfunctions could be complex, there are very few of them. Okay, just so here I've drawn, I think there's a 10 by 10 cube, so there are 100 possible subcubes, but there are only 7 distinct subfunctions. Okay, I've used the same color to denote the same subfunction, to denote the fact that they agree on all points in the subcube. Okay, so for example, all the subcubes denoted by blue, they compute the same subfunction. These subfunctions could be very complex, but the fact is there are only 7 of them out of 100. Okay, so obviously 107 are made-up numbers. Let me try to be slightly more precise. A sense of actual numbers. Consider a random partition of the hypercube into cubes of dimension n to the 0.01. So there are 2 to the n minus n to the 0.01 many subcubes in total, many of them. What Nash-Brooks says is that if you're dealing with a full basis formula of roughly quadratic size, then this induces way less than the total number of subcubes. This is 2 to the n to the 0.99 is a lot less than the total number of subcubes. Okay, so if given this global structure of, if you promise me the function is computed by a full basis formula of size, quadratic size, then in fact it has this structure that, in a random partition, it induces very few subfunctions. For the experts in the audience, this is sort of the contrapositive of Nash-Brooks. We usually think of it as saying if it induces many subfunctions, then you have large formula size. That's like the circuit lower bound point of view. And we have sort of taken the contrapositive to give the learning algorithm. Okay, it's not clear how just this structure alone gives us a learning algorithm, but this is actually where we need to do extra work. So we have a new learning primitive for all functions that satisfy this structure. It says the following. After a pre-processing stage that runs in time 2 to the n to the 0.99, the number of subfunctions, we can learn each subcube in polynomial time. Now, this may seem somewhat surprising because, as I said, these subcubes can compute arbitrarily complex functions. Right? It can be an extremely complex function. But the work is done in this pre-processing stage. Right, so thanks to the pre-processing stage, we can learn every subcube super efficiently, no matter how complex it is. Okay. So given this learning primitive, the result follows quite easily. Well, how do I learn the function? I pay the pre-processing time, 2 to the n to the 0.99, which in our regime of parameters is really negligible. And now we're ready to go. Every subcube we can learn in poly-n time. So the resulting running time is essentially simply the number of subcubes. Okay, I don't have time to go into details, but happy to talk about it offline. So let me quickly wrap up. So that's end of technique 2. Again, this extends to, say, branching programs of size n squared. Okay, as a summary, in this work, we take a new view of learning. We study how much savings can be achieved over the naive runtime. And this is quite a fruitful perspective, and we hope that many new learning results will follow. Just to quickly mention follow-up work, we can learn depth 2 threshold circuits with exponential savings using the approach of this paper. So this is a class that's really at the frontier of our current understanding of learning as well as of circuit complexity. Okay, thanks.
So you extended the half spaces to intersections of...
Right.
But it's all the realizable case. What about extending to the agnostic case, which is
Ah.
a more realistic way?
Good, yeah, we have not thought about that, but that's a great question. So yeah, so that's the next challenge.
What was the question again?
I mean, this is all the realizable case. You only learn functions that are exactly...
No
Oh, yeah,
noise.
the agnostic case?
Right.
Yeah.
Yeah. So there again, we have abundance of hardness results. But still, I'm not sure if the hardness results rules out, non-trivial learning. So that's very interesting.
Is there any relation to the kind of recent result that shows that from natural proofs of lower bounds, you can get learning?
Yeah, I think it's related at a high level. There's obviously a very close connection between lower bound techniques and using the lower bound techniques to get learning algorithms. But one difference, I guess, is here we're learning in a harsh model of uniform distribution-free learning, whereas this new work, it's in uniform distribution, and they get very efficient algorithms, quasi-polytime rather than 2 to the n over, yeah. But this connection between algorithms and circuit lower bounds is present in both works. Yes.
So do lower bounds or conjecture circuit lower bounds tell us how much savings we can actually expect?
Good. So the connection goes the other way as well. There's been a sequence of work starting with Fortnow and Clivens showing that learning gives new circuit lower bounds. So there's an implication the other way as well.
So for the examples you covered, like how much?
Yeah. Essentially, if you beat our examples, if you beating our running time will require new circuit lower bounds via this connection. Yeah.
You get more if you just want to learn the uniform distribution, for example?
Yeah, so the uniform distribution is a lot simpler. Like say AC0 circuits, we have long had, since Linear Mansour and Nissan, we have long had quasi-polytime algorithms. Yeah. And intersection of half spaces, likewise, we can learn intersections of many, many half spaces under the uniform distribution. But in this work, we are concerned with the actual PEG model. Thanks.